Today we're going to be looking at Archimedes Principle. As Rachel said before class, the purpose here is very small. It's just to confirm the Archimedes Principle is correct. So just a brief review of Archimedes Principle. Archimedes determined that the displaced fluid from an object that is in fluid, the fluid displaces, okay? Say that correctly and it works better. The fluid displaced by an object is equal to the buoyant force. Now in class we learned that the buoyant force is the difference, well, the net force that's created on an object because of pressure getting larger as you go deeper in the fluid. So if I have an object in a fluid, I'm going to have a pressure on the bottom. The screen is not on. Okay, so this will show up in a minute. I'm still going to continue writing. The people in Southwestern can see what I'm writing. You have a pressure at the bottom and a pressure at the top. And the difference between those two is what we identify as the buoyant force. So in this lab, we're going to directly measure that buoyant force, and then we're going to compare the buoyant force to what Archimedes said it should be, the weight of the displaced fluid. So that's our whole goal. Now, the weight of the displaced fluid is the density of the fluid multiplied by the volume displaced multiplied by G. So in your experiments, you're going to be measuring the volume displaced, and then using the density of water, you can determine what the weight of the displaced fluid is. And then you're going to be measuring directly what the weight of the object is hanging in air, which would be its full weight, and then the weight when it's suspended in water, which is going to be its full weight minus the buoyant force. So the difference between those is a direct measurement of the buoyant force. And then you're going to compare those. Now, to make sure that it is clear on what you're doing for your scientific method portion, you have to have an observation of something that either floats or sinks when you put it in water. So, it could be, we threw my roommate into the swimming pool to celebrate his birthday, and he floated. And, whatever. And then you could say, now, that was because, according to Archimedes' principle, lay out Archimedes' principle, and then you're going to test Archimedes' principle. So pretty much just like last week with the simple machines, your hypothesis is going to be a basic physics premise, and then you're going to have to test that. And so the way to test it is pretty straightforward. You're going to have the measurement of the buoyant force. Now I'm telling you how to do this. You obviously have to come up and write your own procedure because I don't tell you how to do it for procedure. But the measurement of the buoyant force and the measurement of the weight of the displaced fluid, and you're going to compare those. If they're equal, then you'll have confirmed Archimedes' principle. If they're not equal, then you will have shown that he was wrong. Now, as I said, this has been studied many, many times. So this experiment's been done enough that we know if you don't confirm it, that means you didn't do the experiment right. You didn't, have a groundbreaking discovery. But we have to pretend that it's the, I found something new. So the actual method here, and I'm going to go through the method, it's really simple and straightforward. The first thing you need to do is calibrate your force sensor. So we have the force sensors, just set them up like this, hanging straight down. And to calibrate it, come over here to the Archimedes Principle capstone. It has two displays. It has an actual measurement of the force, and then it does a graph for me as well. I like graphs, so I just have that I use. But you might like looking at numbers. You might look at that. So the first thing I have to do is to calibrate this thing. So I am going to go to calibration on my Pasco capstone software. It should already bring up the force sensor. Next, make sure you have the standard 2-point method for calibration. Click next. And now it says standard value 0. Well, I'm going to start with nothing hanging on it. But before I take a measurement, I'm going to come over here, and there's a button on here, right there, that says tare, T-A-R-E. And what that means is it's going to set it to read 0. So I press that, and now I click to, really, that's not what it was reading earlier when I tared it, so it was actually reading pretty much 0. Well, c'est la vie. That's the light. So I take a reading, and now I'm going to hang a mass from it. Now you notice it says 50 newtons. I am not going to put 50 newtons on there. Instead, I'm going to put 100 grams, and I'm going to intentionally miscalibrate this. What do I mean by intentionally miscalibrate? Instead of 100 newtons, I'm going to hang 100 grams. So while it says the force is in Newton, what I'm doing is I'm calibrating it so it's measuring the force divided by G. Right? I can't actually make it measure mass in grams, but I can make it so it calculates, if G is 9.80 meters per second squared, what the mass is. So it's going to effectively be measuring the mass in grams. So I hang that on there and click set the standard value. Now if you look down here, I can't zoom in, but if you look, it's showing you in this box here, that number that's changing is what it's measuring for what's hanging there. So I'm going to take this 100 grams off and just double check by hanging 50 grams on there. And you can see that number now reads between 50 and 51. Is that perfect calibration? Clearly it's not. And so I might say, well, I need to go back and do it more carefully. I may or may not get a better calibration. For the purposes of demonstration, I'm going to assume that's good and click finish. Once I click finish, it's calibrated. So that's the calibration process. Hit the calibration button again to make that calibration panel go away. Okay, so now that it's calibrated, now I'm ready to take measurements. So I have this mass that I'm going to use. Every person needs to have their own sinker that they're going to do, just for the first part. Then you'll have your test of your experiment that will be different. So if you have a group, one group I think will have 3 people in it, then you'll have to have 3 of these instead of 2 because each person does their own. And make sure you put in the data for each person. So the first thing I'm going to do to start my experiment is I have to make myself a piece of string. I made my string too long, so I doubled it up. Not perfect because we're assuming the string has no mass. If I double it up, I have more mass than my assumed no mass. It's not as ideal. I'm going to actually go ahead and hit start so it's recording data right now. And then I'm going to come over here. Before I start the experiment, notice, when did I tear this before? I teared it just before I did the calibration. I did not tear it between the measurements, right? Because, like if you tear it and you take the first measurement, and then you put the mass on, you tear it again, then your calibration is between 0 and 0. It's not a good calibration. So I just teared it before I did the calibration, and I did the entire calibration without touching the button again. But now I'm going to hit the tear again, just because some of these, especially the older ones, the black ones, those ones drift over time. And so you use the tear button to counteract that drift. So I put it on here, and I need to record what the mass is. Now remember, that says newtons, but I calibrate so it's really the mass in grams. So that number's jumping around, right? That's why I use the graph. I'll take the graph and choose a box and say, what's the average in this box and what's the standard deviation, and use that for my measurement of both the mass and the uncertainty in the mass. I also need to take my graduated cylinder and measure the water level. So I come down here and I look and I say, okay, the meniscus appears to be at 375 plus or minus, and in this case, it's marked off in tens of milliliters. So 375 plus or minus like 2 or 3 milliliters. So there's my first measurement. Now I'm just going to put this in. Drop it in there. Don't drop it to damage your meter, of course. Make sure that you don't have the mass touching the sides of the graduated cylinder. And then I'm going to measure that. Notice it's measuring a lower weight. calibrated as a mass. Obviously, the mass did not change, so you know it's not measuring mass. But it's measuring a lower weight, and so I need to record that, and I need to record the new volume level here, which is about 419 plus or minus 2. So you need to have in your data table recording those numbers. So let's stop this and see if I can remember those numbers. So I had, for my data table, I use quote weight, or I quote weigh it, but it actually was the weight divided by G. So that's units of grams. And then I have the volume in the graduated cylinder, only one L there, in units of milliliters. And I started with 375 plus or minus 2 milliliters. And what was it? 85. Okay. I'm going to put 85 point something plus or minus something because I'd have to go back and read that. And then I have my second weight, again in units of grams, and that was what, 55 roughly? And my second volume, units of milliliters. I didn't give myself room to say in air and in water, but that the first two are in air, the second two are in water. And that was 419. So that's my data for this measurement. Now, for the one that's prescribed, what you're supposed to do is to find the density. So we know that the force buoyant, so I'm just going to add here force buoyant, and I'm going to put force buoyant divided by G. So it's in units of grams. And the force buoyant is just the difference in the two forces. And so I will take those two forces that were divided by G to give me units of grams. 85 minus 55 is 30. So I have 30 grams for my buoyant force, right? And then I'm going to go to my volume displaced, volume displaced in milliliters is equal to the difference in those two volumes. And so 419 minus 475, that's going to be basically 25 and 20 is 44 milliliters. Now you can see, if I remember these numbers right, I got a very bad reading. Because these should have been the weight of the displaced is equal to the weight displaced is equal to the buoyant force, right? Wrong. It didn't float, did it? Because it didn't float, then I don't have the buoyant force is equal to, or excuse me, wait, now I'm getting myself confused. Let's draw the picture. I should have the force of tension, the force buoyant, and the force of gravity when it was in the water. When it was out of the water, I don't have the force buoyant. So the difference in the two force of tensions has to be the force buoyant. So that's where I got this from. The force buoyant is just the difference in those two. And then the volume was just measuring the difference. And so if I calculate the density of the fluid times the volume displaced times G, that's going to be density of water, 1 gram per milliliter, times the volume displaced, 44 milliliters, times G. And so that should be 44. You notice it says in the lab guide, numerically, it's the same number because my density was 1 gram per milliliter. 44 grams multiplied by G should be my density of the fluid times volume displaced times acceleration of gravity. That should equal the buoyant force, which would be 30 grams times G. I have a 50% error of difference here, right? Why? Probably because I didn't remember a number right, or I didn't write down a number right, or didn't measure a number right. So you should not have this kind of error, but that's all that you're having to do actually for your experiment. But what did I say here? Okay, so we've done this, we've made all the measurements. It says to find the density of the object. Well, to find the density of the object is going to be a little bit more, because the density of the object is mass over volume, right? So the mass, I made my first measurement that the mass was, let's actually check and see what I measured for that mass. The mass initially was, turn on that. So 85.72. With my uncertainty, hit that little button to show standard deviation. So 85.72 plus or minus 0.486. Well, if I'm going to record that, what am I going to use for my uncertainty? I'm not going to use the 0.486. I'm just going to use 0.5. They left. So I saw somebody reach to the computer. I was wondering what he's doing. So I'm going to have my mass there is 85.7 plus or minus 0.5 for my mass of the object. So if I come back here,
Someone talk to see if you hear you.
I can hear you, yeah. They came back. You guys hear me? Okay, they're shaking their heads like they can't hear me. Well, I am still broadcasting sound. So, Manawa, you're late, dude. But he can't hear me. Okay. So the mass there was 85.7 plus or minus 0.5 grams. And then the volume I get by looking at the volume that was displaced because it sunk. Because it sunk, completely was submerged, I know the volume displaced is equal to the volume of the object. That's why you have to do this for a sinker, so you know the volume displaced. So in this case, assuming that I wrote those down right and, of course, subtracted correctly, which I'm pretty sure on that one, then I would have that divided by 44 milliliters would give me a density of just a bit under 2 grams per centimeter cubed. So you're going to need to calculate that density and then look up what the density should have been. So in this case, I had a sample that should have stamped on it what it is. If it doesn't have stamped, you have to ask. This one has stamp 5. Doesn't have, but I can tell you by looking, it's aluminum. And so I look up the density of aluminum and compare the density of aluminum to what I got. And I'm pretty sure when you look at the density of aluminum, it's going to be bigger than 2 grams per centimeter cubed, because I'm pretty sure I didn't make very good, careful measurements. But that's the process that you're going to do. So you're going to find the density of this. Everyone has to find the density of one sample. It needs to be a different material for everyone in your group. So I have a group or a whole bunch of samples here. So the sinkers are going to be the ones that are metal. So each person will need to grab a metal one for that part. Now there's not enough metal samples for everyone in the room to get their sample at the same time. At the same time, each group can only do one measurement at a time anyhow. So just make sure you only grab one sinker at a time, do the experiment with that, and then change out. Question?
Do we have to record just the data for our own?
No, you have to record the data for everyone in your group. Okay, one last thing before we go ahead and get started. Because of problems like this where they can't hear me, we're going to try teaching the class in Dick Building 209 starting tomorrow. So for class tomorrow, don't come here to this room. go to room 209 in the Dick building. And I'll try to make sure there's somebody here to redirect you if you forget, because, there are enough people who will forget that you need to have somebody who covers that. Okay, any questions before we get going? Yes.
So for our uncertainty for density,
Yes.
should we have an uncertainty for both the top and the bottom value?
You should have uncertainties in all of your measured values. So you should have an uncertainty in the volume and in the mass. But only in the first experiment of the semester did we propagate that into calculations. So you're not going to have to calculate an uncertainty for your density.